that, you'll get that cancellation with the boundary conditions, right? We go back to here. And in that case, everything still cancels out all right on that boundary term. Okay? So that's the idea, okay, on a bounded domain, okay? Now what about on an unbounded domain, okay? Well, there we go back to our old Cauchy problem we've worked with before, where we have the only thing that we have in terms of an initial or boundary condition is just our initial condition, right? G of x, okay? And on x is in R, okay? And we'll note for G is continuous, okay? Then U will be L infinity, right? And C infinity as well. Okay. So, all right. So then in that case, right, let's jump ahead and let's just define E of t is equal to 1/2 u squared integrated over. Okay. Well, in that case, right, if let's say that u1 and u2 solve the above, right? I'll call it double star or something like that. Here's our double star, okay? Then W equals U1 minus U2 satisfies, right, WT, okay, WXX, and WX0 equals just a 0 there, right? All right, for the, the same reasons as before, you can work this out, right? So this, this functions on X is in R, and then this is in X is in R, and T is greater than 0. Okay. So just our standard heat equation with a 0 initial condition. Okay. Well, then if E of T, let's set that now equal to 1/2, and I'll just make it clear that we're defining this for W of X, right? Then this implies that E prime of T is equal to the integral over R of W, WT. Okay, so now I can use my PDE here to write this as the integral over R of K W WXX XT dx, okay? I'm gonna have to flip to the next page and do an integration by parts, okay? So what's coming up next is integration by parts, okay? And so that is going to be equal to Wx evaluated from x equals a up to x equals b minus, so I need the k up front, k integral, minus infinity up to infinity, okay? And k goes from, this integral goes from minus infinity up to infinity, wx squared xt dx, okay? So now the additional condition you would need, right, is that W and or Wx, right, goes to 0 as x goes to plus or minus infinity, okay? And so that would come from, you know, either requiring integrability, right, of your solution, or you know, because you need so you essentially can't have you can't have solutions U that are shooting off to infinity, okay, as x goes out to infinity, because then you can't properly sort of cancel these things out. So you need this additional condition on the limiting behavior of W and Wx out at infinity, okay? But as long as that's there, okay, then this term here would vanish, and we would have E prime of x, or sorry, E prime of t is equal to minus k, the integral of this, right, which is going to be less than or equal to 0, okay? So again, this implies that the integral from minus infinity to infinity of w squared xt dx is less than or equal to the integral from minus infinity to infinity of w x0 squared dx, right? Which we know has to be equal to 0 because of the initial condition. And so based on the arguments that we worked out before, w equals 0, or in other words, u1 equals u2, okay? So again, we can prove uniqueness as we have before in the bounded domain case, okay? The very last part that I wanted to do, right, is in Rn, right? And so we haven't talked much about the heat equation in Rn. I wrote down the fundamental solution. But let's say that X lives in U, and U is a strict subset of Rn, and it's bounded, right? Okay, so it has some boundary, right? So we'll need some initial conditions for our heat equation, G of X, okay? X lives in U, it's a bounded open set. And it's going to have a boundary condition. And let's just, for simplicity, we'll say U of xt is equivalent to 0 whenever x is just on the boundary of U on t greater than 0, okay? So again, the proof of uniqueness is just going to follow from this energy function argument. There's other ways to prove uniqueness, but we're focusing on energy arguments for now. Let's again define an energy, and I'll take that to be a half the integral now of U squared, okay, over my domain, right? Just like the one that I had in 1D, okay? And so E prime of t, in this case, is going to be the integral over U of U ut dx. And this is equal to k, the integral over U Laplacian of U dx, right? Just because of the heat equation, okay? And now we're going to do an integration by parts in Rn, and we'll apply the divergence theorem. Okay, so now this is what's an extension of what we've seen before. So now we're going to have U, gradient of U, dotted with the normal, ds, minus k, the integral over U, gradient of U, dx, right? So I want you to look at this, right? And this boundary term here, right? It's just the result of multi-dimensional integration by parts. It's just like these boundary terms that we get in one-dimensional integration by parts, right? It follows from multivariable calculus, okay? And And the divergence theorem basically allows us to convert this Laplacian sort of volume integral, right, into a normal derivative through this through the boundary here, right, the flux boundary here. Okay, the integration by parts formula gives us basically this flux term here, and then the integrated by parts formula, right, which is the gradients of u dotted with one another. Okay. Now, what do we know about this term? Okay. Well, if we look, right, we have that u is 0 on the boundary. So this whole thing just goes to 0. Okay. So that means that e prime of t is equal to minus k, the integral over u, gradient of u squared dx. Okay. Again, this thing is non-negative. We're integrating it, and then there's negative sign out front. So this whole thing is less than or equal to 0. So this means that the energy of the heat solution, right, is always going to be less than or equal to u squared x 0 dx, right? So the uniqueness in Rn goes like this, right? We're going to let u1 and u2 solve our IBVP, okay? Then essentially w equals u1 minus u2 solves, right? Wt equals k Laplacian of w, right? Where x lives in u, right? W at x 0 now is equal to 0, okay? And w at xt is equal to 0 wherever x is on the boundary for t greater than 0. So PDE, initial condition, boundary condition, okay? So if I define E of t to be a half, the integral of w squared xt dx, okay? Then based on the arguments that I made before, that's less than or equal to 0, right? Because w of x0 is equal to 0, and this is bounded from above by the integral of 0 again. And so this implies that w is equivalent to 0, and so u1 is equivalent to u2, okay? This is the general plan whenever you are using energy methods to prove uniqueness. Formulate an energy functional. You're usually sort of suggested one, or you should have experience with one from before. You don't know what the energy functional is, you kind of have to make educated guesses, okay? It should usually be even functions of your unknown function or its derivatives, right? And in a form that you can really bring the PDE to use in manipulating, okay? We construct this PDE for the difference between two solutions. It's going to be fully homogeneous. And then you take the derivative, right, of your energy functional with respect to time and show that that energy should be decreasing. So you start off with 0 energy. You should stay with 0 energy forever. And, with the aid of just continuity to make sure that you don't have 0 integrals, but somehow you have, some non-zero function inside, you can show that the integrand has to be 0 too, okay? So that's the end of the discussion on energy functionals. On Monday, we'll start talking about, we'll take a little bit of a detour into Fourier transforms, and then we'll start talking about what's called the maximum principle for the heat equation. This is another tool for proving uniqueness, and it also gives some nice solution properties. And then we'll talk about well-posedness and Duhamel's principle. So going into a little bit more detail on tools